All right, here's where mass percent becomes really important. Mass percent allows us to get empirical formulas for our compounds. So let's take a look at this. So first, take a look at mass percent. So we've already kind of calculated what it is, but we have many analytical techniques / instrumentation, and they can tell us the mass percent of a sample. So for example, if someone hands you some kind of powder and you have no idea what it is, one thing that you could do is you could use an analytical technique that'll tell you, oh, this is the mass percent of that compound, right? It's 80% carbon, 20% hydrogen, right? It can tell you the mass percent. And if we have the mass percent, we can then use that to calculate our empirical formula. So let's take a look at what empirical formula is. And so empirical formula is the molecular formula reduced to the lowest whole numbers. So for example, hydrogen peroxide is H2O2. Notice that they're both divisible by 2. So its empirical formula would be HO. Right, and that's what we could get from the mass percent. Another example is C6H6, right? They're both 6s. That could just be CH. P4O10, right? They're both divisible by 2. So you go down to P2O5. Note that you can't reduce this any further because 2 and 5 don't have any common number that you can divide them by to receive a whole number, right? And so that's the cool thing about mass percent is they can tell us the empirical formula, and then with some other techniques, we can actually find out what an unknown is, right? And a big part of chemistry is, hey, here's something, we don't know what it is. You as a chemist, tell us what it is. So let's take an example of this. So we analyze a sample and find its mass. Percents are it's 60.00% carbon, 4.48% hydrogen, and 35.53% oxygen. What's the empirical formula? And so we're going to go through this step by step, and if you follow these steps, you'll get to the right answer. Sometimes these values are given to you as percentages. Sometimes they're given to you as grams. Grams are more useful. So if you're already given in grams, you can skip this first step. If they're given in percentages, the first thing we're going to do is just change the percents to grams. And the way that we're going to do that is we're just going to just change the percentage to a gram. We're going to keep the numbers exactly the same. So instead of 60%, we got 60 grams. Instead of 4.48%, we got 4.48 grams. Instead of 35.53%, we get 35.53 grams. The reason we can do this is that percentages are just ratios. And so percentages are a ratio out of 100%. So we just assume that we have 100 grams of sample. But it doesn't really matter too much. All right, after you've got the grams, the next thing we need to go from grams to moles. So we need to go from grams to moles, and then to do that, you're going to have to use your periodic table to find out the molar masses of each component and figure out how many moles of each we have. So for example, for the carbon, we have 60.00 grams of this carbon. And we're going to use the molar mass that we find on the periodic table, which will be approximately 12.001 grams per mole, to go to the moles of carbon. So then we end up at 4.995 moles of carbon. And then we're going to do that for each component. So for hydrogen, we have 4.48 grams of hydrogen. We're going to use the molar mass, 1.008 grams per mole. Do the math, you get 4.44 moles of hydrogen. And do the same thing then for oxygen. You have 35.53 grams of oxygen. Take a look at oxygen's mass on the periodic table. You get 15.999 grams per mole. You end up with 2.221 moles of oxygen. So what we've done is we've converted the grams to the moles. And then if you think about the chemical formula, that's by count, which is what moles are. So step 3 is to write your formula with these kind of weird numbers, right? So we're going to write C, we've got 4.995. We've got H, we've got 4.444, and then we've got oxygen, which is 2.221, right? That's obviously not an acceptable chemical formula, because when we have chemical formulas, they all need to be whole numbers. Can't have part of a element. In the 4th step, what we're going to do is we're going to reduce this number by dividing by the smallest number. So what we're going to do is our smallest number is this 2.221. So we're going to divide each of these by 2.221. And then we're going to write out what we get. So we get carbon, in this case, it's 2.25, hydrogen 2, oxygen 1, right? So we're getting a lot closer, but note this is still not a whole number. So this is still not an acceptable way to write a chemical formula. And so in our step 5, we're going to get whole numbers. And we're going to do this by multiplying. So for example, we have this 0.25. If you think about how you get 0.25 to be a whole number, you have to multiply it by 4. If this was, a 0.5, you would multiply it by 2. Whatever you need to multiply that to get to a whole number. But you have to multiply it by the whole formula. Otherwise, you're going to change the identity of your compound. So we're going to multiply this whole formula by 4. And then what we get is C9H8O4, right? You notice I multiplied the whole number by 4. And what you'll notice is that none of these numbers have a common divider, right? So this is as reduced as we can get it. And so this is our empirical formula. Right, so you had some kind of unknown compound given to you. You ran some kind of analysis to find the mass percent. You did the math to get the empirical formula. Now you have a better idea of what your compound is. And so this is the empirical formula. So the real formula, it could be C9H8O2, or maybe it's C18H16O4, or maybe it's C27H24O6, so on and so on and so forth. So we've reduced it down to, certain number of options of what it could be. But in the next part, we'll take a look at what it actually is.